Okay, so that principle of using small, slow solutions is an important one. It's a very smart strategy to implement. Number 4, slow, spread, and infiltrate the flow of water. Slow, spread, and infiltrate the flow of water. Calm the flow of water to reduce destructive erosion, and increase, that should be increased D time, that's not E time. Increase the time and distance the water flows. This will increase infiltration into the soil from source, right, high point, to sink, the low point. This practice achieves wide distribution of water throughout the watershed. So the infiltration is if you can do any of the strategies at all, infiltration is the one that you want to put into use. That's the one that will get you the most bang for buck. And again, it's infiltration. Most notably and importantly, it's infiltration that allows you to grow something. Right. So it's one storage of water that allows for the establishment of another storage of water. Okay, so here's the figure. All right, so the zigzag and calm the flow path of water to reduce destructive erosion and to increase the time and distance that the water flows. Right, the zigzag. Right, so this is what will again give you the best outcome. Yes, sir.
But isn't there a certain sort of contradiction or competition between, on the one hand, the slow spread and infiltrate approach, and on the other hand, the trying to have a store of water where you actually collect it, which is the opposite of spreading it out, to have then water available to strategically, let's say, drip irrigate at a particular time of year when you're lacking it. So it almost seems like there's two separate messages. The one is spread it out over the landscape, the other is bring it together in one point to store. Did you use it at the time?
It depends on the context, because you might have a part of the land that's actually on a slope, an area that allows for you to again store water up high, and then maybe down low. The strategy would be to infiltrate the water down low, maybe in the flatter, more shallow slopes, because those are likely the places that you're going to have, say, be your primary productive areas. And the reason why you want to store water up high is because then you can use gravity to send it down to those lower areas where you would ultimately want to infiltrate the water, again, to create some kind of growth. So again, they're not working at cross purposes. You're sort of using one to enable the other. You're using the storage to enable the infiltration. So they're working in concert. They're not necessarily working at cross purposes. Amen?
Yeah, I just want to say you also want to do maybe both if you have a bit, like quite a bit of land, and you only use a really small part of the land, really have some plants, need drip irrigation, all these kind of things. But for the rest you try to increase the groundwater levels. So in most of the part you won't want to have spares and everything which is infiltrating, but you also need one part of it separated.
Yes. Because I mean, so I understand you can have both, but like it seems to be sort of, it is kind of opposite approach, like either store which needs to concentrate for a big area in one place, or to spread it out.
But you can store it and then spread it out.
Like you're storing it to spread it out.
Where you want to have it by your irrigation system.
Yeah. You're storing it so you can spread it out. That's basically it.
Yes.
It's storage to spread it. And again, depending on, it's going to be very sort of context specific. Like you might have a situation where, and I want to pull up a figure to show this. You might have a situation where you need to implement a plan that allows you to get again those high storages, because you don't have the access to equipment or the energy or the labor to move water from one place to another. So you have to be a lot more smart and intelligent in how you plan your storage. Actually, that's the figure I want to see. So if we look at this illustrates a great deal of what it is that has to be overcome. So if you look you know, on your left, right, this problem that has to be overcome in many cases is compaction, right? The compaction is what's preventing oxygen in water from getting to the roots if we're talking about vegetation, but it's also preventing, again, that through flow and that recharge of groundwater if we're talking about, you know, wanting to recharge aquifers and replenish what's being pulled out. Now, the way to think about how the storages work is it's sort of like you have three different means of storage or three different sources of water. And it's not a matter of favoring one or the other. It's a matter of basically creating a link between the three. So you have what I like to call blue water, brown water, green water. Right? So the blue water is, again, what falls as precipitation. It's the water in the atmosphere. That blue water eventually can be turned into brown water if you can get it in the soil or get it in the ground. The brown water eventually becomes green water if it can be taken up by vegetation. And then eventually the green water becomes blue water again. Right? So it's like the legs of a race. Right? It's the links in a chain. So you're just trying to create a means for that link to be made. Blue to brown to green, and then back to blue. The problem now is that cycling has been broken because the condition of the storages has been made worse. The availability of the storages has been made worse. So you don't have the brown, you don't have the brown water because the ground's too hard and you can't get the blue water into the ground. You can't get the green water because, again, the brown water, it simply isn't there. So the nexus point between the blue and the green is the brown, right? That's the storage that you actually have the most control over. So if you can prioritize trying to do something about the ground, about the condition of the soil, then that's what actually reconnects all of the different varieties of storage, and then you can actually start getting some kind of, you know, outcome again that is more to your favor. All right, back to the list. So that was 4. Number 5, always plan an overflow route and manage that overflow as a resource. So always be prepared for overflow. It is often rooted and used to passively irrigate nearby vegetated earthworks or sheltering vegetation. This also illustrates the importance of the 4th principle, slow, spread, and sink. So one of the things that is often included in this discussion about earthworking and the management of water is the use of what we call a spillway. Right? So spillways, I think you guys have seen some of the spillways, or there should be spillways on the swale features or on the dam. Right? So there's a point when, say, the dam fills up and then the excess needs to go somewhere. So, for example, with the swale, the last place you want it to go is over the berm. Because if you get a lot of water starting to run over the berm, then you get erosion. Right? It starts wearing away all the soil, and then it washes away. If you have water, say, overtake the wall of the dam, that's another no-no, because if you get enough water flowing over the dam for long enough, the dam fails, right? The wall fails. Or if the dam wall isn't built properly and you have water start to seep through the wall fails. Right? So being able to manage the excess is often a key to the long-term success and the long-term viability of whatever means of storage you have in mind. The fact that we saw the type of erosion on some of the swale features is an indication that the way that the overflow is being managed, that needs to be improved. Because right now the overflow is actually is causing more erosion in some of the areas on site. So that has to be something that's actually managed better. So here, if we look at this figure, If we do the whole exercise of, okay, let's start at the top of the watershed and go all the way down to the bottom. The top of the watershed here is what? The roof, right? The roof. So the water enters in, first thing it contacts is, again, the tallest figure here. Well, in this case, the tallest object is either beside the top of this tree or the roof of the building. So we'll just call it the roof. So the water goes into the gutter. That gutter fills a tank, right? It fills the cistern. Fills up, and then eventually it goes to overflow, right? So it overflows into the pipe. That pipe is then directed to a basin. Right? That basin is planted out to a tree and is filled with mulch. That basin eventually fills up, and then the overflow then goes to this diversion drain, right? And it's lined with stone. Why would it be lined with stone?
Catchment? I mean, to catch like some kind of debris or whatever.
But there's something specific about the use of the stone and the flow of the water. Why would you use it? Right, Rachel? Were you commenting about this?
Yeah,
Well, I was going to answer something. I'm sorry. I'm there? Yeah, right, erosion. Right, so the stone is able to withstand the movement of the water, right, the shearing. It's much better suited to withstand the shearing caused by the water in the soil, right? Because if you don't, and you'll see it, you've seen it on, the places on, the camp where you can see where there hasn't been any use of stone or plans have been made to manage the flow of water. You start to get scouring, right? The water will begin to erode some of the soil. So the use of stone on the spillways is a way of being able to prevent that from happening. And then you'll see it continues to go from basin to basin to basin, right, as it overflows and fills up each of the features. And then that in turn is going to another opportunity to be able to establish vegetation. Yeah, Mark?
To stimulate sinking in?
Right, exactly. So the whole point is that you're sending it to each of these places in the hopes that you will eventually be able to infiltrate it back into the ground. Right. Right, exactly.
One risk I see with this kind of approach is that this is something that designs in the beginning and it's all nice and good, and then that big overslope which was designed doesn't happen for the first 5 years, and then eventually there's a ditch and you start dumping stuff into it, and that ditch dumps stuff into it, so that by the time it actually then comes to the 1 in 10 year massive rain, it doesn't work as designed anymore
because you filled it up.
It's a piece of functionality that it runs a high risk of losing functionality because it is used very irregularly.
Well, the whole point is you have it in place because you've got some certainty that big event that you just spoke of is going to happen at some point.
So
the problem is if it happens and you're not ready for it, and whatever comes from you not being ready for it, all you need is one bad year. You need one bad year.
So does it mean that you have to sort of almost like every year go and check your emergency water?
Absolutely.
Infrastructure?
Absolutely. I'll give you an example. Maybe I'll try to pull up the video clip. When I was at Jeff's farm in 2009, they were in the middle I think they were kind of just getting to the tail end of a decade-long drought in a lot of Australia. It's a really bad drought. During the season, the rainy season that I happened to be there, they had, at that point, there were 2 of the largest rains that they had in 35 years. What happened on the farm? Now, the tricky thing about his place is it happens to be, I'm going to see if I'm pulling up an actual layout of his property. At the bottom of the property, there's a river, there's a stream that runs past that separates his place from the adjacent property. The banks of that river in that rain filled up and it completely submerged the bottom paddock of the property. Like, as a matter of fact, there was a tree on that low part of the property, probably as tall as this roof, and the water had to be about 1/3 of the way up the tree, at least. And that was from the river overtaking the banks. And then all of the other things on all of the other bodies of water he had on the property, all the other storages. He had dams and he had swales that were attached to them. All of them were overflowing. But he was able to design it such that the overflow was handled. It didn't end up becoming, something that was destructive or catastrophic. But obviously in some places, he didn't make the spillway wasn't necessarily big enough, or there were certain things that needed to be done to make sure that when water was pouring out of them, it wouldn't cause the feature to erode. So there was some repair work that had to be done in order to, get them back into working order. But for the most part, it worked. It worked. So those are the kinds of things that, when you see what happens when you're prepared, and you see what happens when you're not prepared, it just, it imprints on your mind the importance of this particular point of planning and overflow.
I don't know if it's tested too much, and people have been there yesterday, they have also seen the grey water system, how to design it, but like Keith was explaining it. I just wanted to add that was also one of the big challenges. What if you have this, that every day there are like 10 people and you construct showers, so 10 people are going to shower every day, but what if there's then, okay, not everyone is showering every day, but let's say everyone is showering once a week, and then you have a weekend or like a week where you invite up a group of 30, 50 people who are going to do workshop there whatsoever, and then you still going to use the same showers.
Right.
And that is not like a natural event that's going to come up, so the showers need to be able to have it there for having, otherwise everything is moldy and the people are going to die in the wet.
But this is where
having a bypass.
Yeah. I mean, this is where the principle of like over designing comes into play. So usually, like in engineering work, usually when you're designing something, you design for a factor of safety, quote unquote. So usually you'll over design it maybe to a factor of 2 or 3, meaning you're expecting to experience a load or stress that would be 2 or 3 times the stress or the load of normal usage. So that way, you never get to the point where the design is overtaken, where it's overwhelmed. So it's more than you would typically need, but you're also planning for what may possibly occur in the future to where it would have to withstand a certain load. So with regard to, say, the gray water system, based on what you anticipate as being a potential load in terms of usage based on how many people are showing up, then you would, in the beginning, you would actually plan for designing with the possibility that 50 people or 100 people or whatever were going to show up to the site, because you're sort of projecting, okay, this is kind of where we're headed. This is where we want to be. This is where we want to be. Like, you are wherever it is that you are, but we want to be in this place to where we can handle having 50 people on site and have not be a problem. And so that's a consideration at the very beginning, that needs to be kept in mind. Okay. So that's 5. Plan for overflow.